Hey everyone, welcome back to the channel. In this video, I want to talk about two complementary patterns that support high availability. One is called failover and the other is called replication. Under failover, I'll talk about two sub-patterns. In under replication, I'll talk about two things also. Then after that, we shall look at availability patterns. This video is video number 6 in the series where I'm teaching you everything you need to know concerning system design, from what is system design to designing scalable and high performance applications. Under failover, we have the active passive failover. I'll just copy this, replicate it just down here, maybe give it a different color. So it's called, probably reduce the font size a little bit, active passive failover. When you have two servers, server A and server B. Server A is referred to as the active server, and server B is referred to as the passive server. Server A is called the active server because it's the only one that handles the requests. Meanwhile, server B does not do anything. It's only waiting on standby. So between server A and server B, there is a message that is sent between these two servers. And this message is called a heartbeat. Simply a ping to make sure that there is communication between the two. One letting the other know that yes, I'm up and alive. In the event that the heartbeat stops, server B knows that server A is now down because there's no more communication. And then server B takes over the IP address of server A. So if server A was IP 192.0.0.1, server B takes over the IP address. And then it becomes the current active server, which means it will be the server handling the requests. Of course, when this happens, there's some kind of downtime. But the downtime depends on the standby mode. There are actually two standby modes. There is hot standby mode, and there is also the cold standby mode. So the downtime depends on the standby mode of the passive server. Hot means that the passive server is active and fully synchronized, ready to take over. And because it is in this hot mode, it takes a short time for it to become the active server. But when the passive server is in the cold standby mode, it simply means that the passive server is either inactive or powered off. And because of that, it will take some time. The downtime is longer. This might be longer, but it has advantages. When a passive server is in the cold standby mode, it's actually cheaper to manage because it's not consuming the resources. But the caveat is that it takes longer. There's a lot of downtime. But with the hot mode, you have less downtime. It's actually almost instantaneous, but because it's always on and active waiting to take over the job of handling requests, it costs more because it's consuming resources always. The active passive failover is also called master slave failover. The other type of failover is called active failover. In active failover, we also have a very similar setup. We have two servers, but this time, instead of only one server being the one to handle requests, like in the active passive, we have both servers handling the requests. Server A handles requests and server B handles requests. In the event that these servers are public facing, then in this case, DNS needs to know the public IP addresses of server A and server B. And of course, they have to be different IP addresses. If you want to understand DNS, IPs, and so many concepts, check the link in the description, which points to the playlist that shows you videos that come before this video. I talk about DNS and IPs in much more detail. So with the active failover, when the servers are for internal use and they're not public facing, then your application logic needs to handle the routing between server A and server B. This active failover or active passive failover is not the best you can call it. It has a few disadvantages that I want us to look at. The first disadvantage is that in case your active server does not come up immediately, there is a risk of you losing data. During that time of the downtime, there's a chance that data which has just been written to one server is not replicated to the other server immediately. And because of that, you can lose data. And the other obvious disadvantage is that you get to have extra hardware. Before we talk about replication, I think I forgot to tell you that active failover is also called master failover. Now, in replication, we have also two sub patterns. I'll copy this over here and maybe drag like so. So we have replication only. So with replication, we have a pattern called the master slave replication. Do not confuse it with the active passive failover. Your mind should be focused on thinking about the concepts, not thinking about the names. I repeat, your mind should be focused on thinking about the concepts, not the names. Why do I say this? Thinking about the concepts makes it even easier to remember the names. Okay, so let's look at master slave replication. In master slave replication, you have a master node. I'll use probably a different color. So this is your master node. And this master node serves reads and writes from clients. So I'll say this is a client. And this client is going to receive reads and writes. So this is the master. And this arrow is representing either a read or a write to the master. Once this takes place, this master replicates that data to another server. This one is called a slave. And I want you to know that you can have more than one slave. It could be one slave, two slaves, three slaves, depends on your need. And in turn, these slaves can also replicate to other slaves. Do you see what this is forming? It is forming some kind of like tree hierarchy. So by explaining this, I hope you already see the difference between master-slave replication and master-slave failover. Do not confuse the two. So here I have other slaves who handle replication. Wow, drawing this thing is giving me some work. So this is slave and another slave. So how this happens is that now other clients, so you can have a client, I'll say C for clients. So C is a client. We have another client here. We have another client down here labeled with C. So this client could make a read from this slave. This client could make a read from this other slave. This one could make a read from this other one. Okay. So just know that the slaves handle read operations. Clients do read from the slaves. The master can be also read from, by the way. Okay. Or written to, but mostly handles writes. Now, in the event that this master goes down, we can stay in a read-only state. Why? Because the master is down, our setup cannot handle write operations, and therefore we can only read from the slaves. So It remains in a read-only state until we either upgrade one of the slaves to a master or entirely create a new master node. That is what master-slave replication is all about. The disadvantage of this is that we need logic to be able to promote the slave to a master or to handle that kind of transition, whether to create a new master or a slave to a master. And the best way to say is we need additional logic, not just logic, but additional logic. Of course, this is not the only disadvantage of master-slave replication. I want to talk about other disadvantages after I've talked about master-master replication, because the disadvantages I've not mentioned apply to both master-slave replication and master-master replication. So let's discuss master-master replication. And again, do not confuse it with the master-master failover. If you don't remember master-master failover, please check it out. Look at the past section in this video to understand it, because I know some of you might be skipping sections entirely. All right, let's get into it. So with master-master replication, I need to change this to master-master, not master-slave. So with master-master, we have our master. So this is master server and another master server. I'll label them with M to represent a master server. And maybe it's just their in-house setup, okay? Then we have clients, client C again, and another client C. So with master-master, client C can send either a read or write request, and also this other client can send a read or write request. So the point is that with master-master replication, each of the nodes handles both reads and writes. And then the masters work together to handle the writes and make sure that everything is synchronized. But I'm sure you already see the issue with this. It comes along with some disadvantages. The first one is that you must introduce a load balancer. If you don't introduce a load balancer, then you have to handle the routing in your application logic, which is still extra work. Another disadvantage is that most master-master replication setups are either loosely consistent or they have increased latency because of synchronization. And the first part I talked about, which is being loosely consistent, validates the ACID rules. Okay, it validates, not validates, but violates ACID. I'll talk about ACID very soon in a future video. Make sure you follow every video in this playlist. Another disadvantage that can be a pain is when you have to deal with conflict resolution in a master-master replication setup, especially when you're growing and you're adding additional nodes. Let's now talk about disadvantages that apply to both the master-master replication and the master-slave replication. One disadvantage that comes to my mind, and if you think about any disadvantage and I've not mentioned it, please leave it in the comment section. Think about this. If a master goes down before the data which has been written has been replicated, you suffer loss. As simple as that. Also, when we have so many writes, the read replicas get bogged down with replaying those writes, okay, to their own storage. But that comes at a cost of the read operation. Remember, writes are being sent, so those writes have to be replicated. So the read replicas have a bigger task, okay, of handling those new writes than doing their job which is intended for reading. I don't know if you get it. Remember, you are a slave, you're supposed to serve reading. But if there is a lot of writing, then your focus goes on the writing and replication than serving the reads of those writes. As simple as that. Then, of course, like I mentioned earlier, this introduces extra hardware, meaning more complexity. As simple as that. In some systems, writing to a master spawns multiple threads working in parallel. And yet, the read replicas are handling the writing in a sequential manner. That's kind of tricky. It's time to talk about availability in numbers. A whole year has 100% availability. That is if everything goes well. But availability is actually measured in nines. So you can find 3 nines like 99.9%, 99.99%, which is 4 nines. How do we come to the numbers in this table? Let me explain to you. When you see this 99.9%, it simply tells you how much your system is available in a year. Meaning that out of all the time, your system is 99.9% available. You're trying to answer the question, out of all the time that is available, how much of that is the system available? 100% minus 99.9, you get 0.1%. This is the downtime. That downtime in a year translates to 8 hours, 45 minutes and 57 seconds. 0%, not 0%, but 0.1% in a month translates to 43 minutes and 49 seconds. Not 49 seconds, but 49.7 seconds. 0.1% translates to 10 minutes and 4.8 seconds in a week. In a day, it translates to 1 minute and 26.4 seconds. If you go to the 4 nines, you see that we have less downtime. So the more nines you have, the less downtime. We see that with 4 nines, we only have downtime of 8.6 seconds in a day. And in a year, 52 minutes. So consider this very carefully. If your downtime is 99.9, meaning 3 nines, if you have 3 nines, it means in a year, your system can be off for almost a full working day. Because the full working day has 8 hours. And the downtime of 0.1% in a year is 8 hours, 45 minutes, and 57 seconds. I hope you've understood this. If it's not clear, let me know in the comment section. I can organize a live stream or answer you in another video or even in the comment section. When you have components in a service and these components are not having 100% availability, their availability depends on whether they have been arranged or set up in sequence or in parallel. If you have services, 2 services, okay, service A and service B, and they have been arranged in sequence, and each of these services have an availability which is less than 100%. And for example, let's say service A has availability of 99.9% and service B has availability of 99%. To get their full availability, and let's say the first service is called service full, not A, and the second one is called service bar, not B. Okay. To calculate their total availability, you get the availability of the first service multiplied by the availability of the second service. And in this case, we would get a 99.8%. Then, if those components in the system are set up in parallel, to calculate the availability, we shall use this formula here. Okay, so this is trying to bully me. Let me drag it right. Looks like I'm losing control. Let me do it right. Just a moment. Okay, get it back, drag it away. All right, this looks better. So this is when, for example, if service full has availability of 99.9 and service bar has availability of 99.9, then you'll do a 1 minus, into brackets, 1 minus that 99.9 and multiply it minus 1 minus 99.9%. That would give you about 6 nines, okay, which is 99.9999%, okay, which is very, very high availability. So the point is this: when components are arranged in parallel, availability increases. When components are arranged in sequence, availability decreases. As simple as that.